I want you to listen carefully and really understand, and you're going to actually implement this in that next assignment. And I want to go through this again, and if you have questions, I'll be glad to answer. So support vector machine has lots of applications in pattern recognition, computer vision, and computer vision object classification and detection. That's what you're going to write a program about, and action recognition, and many different areas where the problem is to classify given image, given video, given feature vector. Then you use a support vector machine. It's a classifier. Okay, and that is one thing which has really impacted a lot, many areas in computer science, machine learning, AI, computer vision, image processing, and so on. It's a big impact of this, and it's a pretty elegant formulation, and it really works. So it basically works with that you have to train a classifier, so it will use some training examples, and it's a discriminator classifier, which means you will have positive example and negative example, and will learn to discriminate between those two. Okay, and that learning is in terms of the regularities, in terms of these margin or boundary between these two classes. So once it is learned, the classifier is learned based on training examples, then you have an unknown example which you don't know what it belongs to which class. It will classify correctly. So that's the idea. And so the example is human detection, that given a window of an image, we want to say, is there a human or not human? And we will get positive examples and negative examples, and we will learn a classifier. Then once it's learned, then we can test it, that we don't know if there's human or not. The classifier can tell us it's a human or not. So that's the idea, and that's what you're going to implement. So as you remember that we went through the how to compute the HOG. So in order to learn a classifier, you have to input a feature vector. It's a vector. It can be arbitrary length vector, and it is going to classify these examples, running example, based on the feature vector. Okay, and the feature vector which you are going to use is HOG. And as you remember that we have these blocks and we have these cells and all those things. We look at the orientation, the gradient orientation. We divide these in bins, 9 bins, and we get a histogram, and all these things you already know, and we have done this many times. So the main thing we are going to do here is to talk about how we learn this classifier. So you will do this in RIA dataset in your program. Yeah.
Each cell should be 8 by 8 size.
Yeah.
8 by 8 you mean pixels?
Yeah, 8 by 8 pixels. Yeah. So in this there are 1208 positive windows, and 1218 negative windows where there's no human. In the upper row there are humans, and you compute the HOG, which looks like that, and the vectors like this. And these are more examples. These are slides from Andrew Zisserman, Oxford. And then you can take these positive examples and average them, and the average person may look like that. And these are the ages, and this is the HOG. As you see, there's a HOG histogram in terms of the orientation. It shows you the direction where you have the highest peak. And if you look at carefully, it looks like actually person. There are arms, there is body, and so on. And so what boils down to, we have a feature vector, which is the d-dimensional feature vector, and it can be HOG, it can be SIFT, it can be anything you want, but we are going to talk about as a feature vector, and we learn the classifier based on feature vector. So what that means that we are going to learn this hyperplane, which is the W transpose X. W is a vector, X is X vector, X is a feature vector, and B is a scalar. So once it's learned, then we can classify, and we can say there's in this window there's a human, in this window there's a human, and these are the confidences. So now this is a classifier we learned, a linear classifier. Yeah.
The HOG, before the calculating the HOG feature, the window, how do we detect the window?
Yeah, so for the training, the windows will be given. So you are given the windows for the training example, positive example, negative example. You
but,
just
if we given a
test.
Test.
Yeah, test. You look at each possible window. You will do the search. Okay.
You're talking about it's been given, so basically the image is the size of the window.
Yeah.
Okay.
Yeah.
So we only
Just compute that. Yeah. And then you will given a big image, for example.
Yes.
Then you will just look at each possible window. Say, is there a human? Is there a human? Is there? That's the way. It's called sliding windows.
Edge feature to roughly detect the possible position and then calculate the.
No, I mean, let's just follow what the assignments say. Edge features, you are going to do what? Like you will detect edges first, and then what?
At first, use.
Yeah, I mean, you can try that. You just, okay. So let's continue this. So we are going to talk about the linear classifier. So we have these data, and we are going to assume, just to understand, the feature space is two-dimensional. Feature vector is two-dimensional because we can visualize it. Otherwise, the feature vector can be 3,000 dimensional, not as many dimensions as you want. So we have here these examples, and so these are the positive examples, and these are the negative examples. Okay, so this example has the x1, the first feature vector, component is this much, second is this one, and so on. And this one is x2 is small, x1 is large, and so on. So these are the two classes. So what we want to do, we want to come up with a line which can separate these two classes. And the line in 2 dimension, and the plane is 3 dimension, and hyperplane is n dimension. Okay, so this is the equation of a line or the hyperplane, where we have the W is the parameters of the line, which will be slope in 2-dimensional line, and then X is the feature vector, which is the value of these little things, and the B is that bias, or B is that scalar thing. So we want to find this line, and such that if it is greater than 0, then this is positive, less than 0 it's negative, and this will separate. So that's a pretty simple, intuitive way to talk about that. So which means we are going to learn this function which will depend on X, which is a feature vector, W, which is a classifier. We'll learn W and B, and if this is depend on the given unknown vector, we will look at this and look at the sign. If it is positive, then it is the this class. If it is negative, this class. So that's the idea. Now the question is that how do we find this line? Because there are lots of possible lines, and we want to find out this line automatically, okay, by using a computer program. So that's the hard problem. And suppose we can come up with this line here, but then there may be some misclassification. This actually should be on this side, but it happened to be, because we picked this line, it was misclassified. But this may be a good line, which will fix that. So instead of a line, therefore, we want to look at a margin. we want to look at a thicker line, a margin, which will separate these two classes, and it's a linear classifier, and we have a width of this boundary, and we want to increase that as much as possible so that it hits the examples, and we'll have much better time in classifying as compared to when you do it's a one line. There can be misclassification. So so that's what we want to do. So then these lines, our margin will be defined by these examples which are shown in the red, and these are called the support vectors because they are supporting this margin, and that's why it's called support vector machine. This classifier is called support vector machine. Okay, so we want to maximize the margin, and once we get the margin, then we can actually forget about the rest of the examples. We just worry about the support vectors, which is another nice thing for the support vector machine. Yes?
So when we're actually doing the testing, we'll still rely on the line that's in the middle of the margin, right?
Yeah, I mean, we will rely on the W and B. I'll show you how to test it, but main point is that we will have W which will describe this margin, and that can be described only based on these examples which lie on the margin. So we don't have to remember the other examples, even though to find the margin we have to use all of those. Okay, so because see that once we know the W, so the whole idea is we know the W, we have to compute W, which is the margin. Yes, and then to test the example we just put in here for that particular X, we know the W, we know the B, we can define it's a positive or negative. That's it. That's the testing. Okay, did you follow? So the whole idea is we want to find W. We are going to talk about how to find W and B. So that's called learning a classifier. So we will learn that. So once we know that, then we are given a test example. Then we will substitute in this. We know the W, we know the B. The X will be the test example. Then we look at the sign.
But the W and the B is just still a description of the line inside.
Yeah, I mean, this will describe the margin. The way we are going to put a constraint, it will be a margin.
But if we get a sample that's inside of the margin, but
yeah, I mean, so we want to avoid that it should not be in that. It should be either this way or that way. So we want to separate as much as possible so that we can clarify that. Okay. So now we want to separate these classes, and this is the equation of a line, and these are the two other sides. This is positive, this is negative, and we're looking at signs that. Let's repeat. So in that, we are going to use these very simple concepts which will help us to understand. So one is that we want to look at the perpendicular to the plane or perpendicular line, this line here. Okay. So now if you look at 2 points, one is say x prime on this line, that is x double prime, then they lie on the line, so therefore they should satisfy this equation. And same thing, we can subtract them like this, and then we can rearrange this. The B will cancel with B, and then W can come out, and this x prime, x double prime. Now this is a line from x prime to x double prime, because 2 points you connect and become line, and so this is a vector, and this is another vector which is a W, and so this is a dot product of 2 vectors. It's equal to 0, which means W is perpendicular to the line. So that's one thing you need to know, which we are going to use. Second thing is that we want to look at a distance from a line to the plane, which is shown here, and that suppose that's a point, and we want to find a distance from this point on this side to this one which is separating them, which is x, and this distance we want to find in the direction of the W, which is perpendicular to this line. So again, we are going to use a unit vector, which will take the vector and divide by magnitude, and then we want to find the x minus xn, and this is a distance, and we want to project that in the unit vector w hat, and this is the way it's going to happen. And we can simplify that, take the 1 upon w outside, so it's wx minus wxn, and then we can add plus b and minus b. Then we can say that, well, this is equal to 0 and this is equal to 1, so absolute value of this is 1 upon w. So therefore distance from a point to the plane, a line, hyperplane, is 1 upon w. So that's the second thing we need to do, use. Then third thing is that we want to look at the margin. So it's the distance from this line to this line in that direction of w. So again, we'll take the one of the point on the red, x plus, another point on the blue one, x minus, and then we want to find that margin in the direction perpendicular to this, which is w hat. So this is x plus and minus x minus, and we project in w hat. It's the same thing. This is a definition of unit vector, and then we open this up, and again we add plus b minus b, and then rearrange this. We take the minus out here, so it'll become wx minus plus b, and we know that this is 1 and this is minus 1, so it'll become 2, so 2 upon w, which means that the margin, the width of this margin is 2 upon w. W is the plane or line which is going through that. So that is going to be very crucial. We are going to use that. Okay, so now, so linear SVM basically is that we want to correctly classify based on all training data. So these are your things, just repeat. If it is plus, it should be greater than 1. If it is minus, it should be less than 1. And this we can rewrite like this. So it's, instead of 2 equation, we have 1 equation, yi, because this is plus 1, get this one, minus 1, you get this one. And so these are the constraints. So they have to satisfy this constraint. At the same time, we want a bigger margin. Okay, so we want to maximize the margin, which means we want to maximize 2 upon w. Okay, and which means instead of maximizing 2 upon w, we are going to minimize w upon 2, which is this one. This is the magnitude. So this is a dot product of these two vectors. So maximizing this is same as minimizing this with the constraints which are shown here, and that will become a quadratic function, because you take a vector, find dot product of itself, it's a quadratic terms. You say xy and xy, x square plus y square is quadratic, power 2. So then these are the constraints. So in a way, you can just use this in your quadratic, programming, command in MATLAB. It should do that. It should find you the w and the b. So that is the starting point, which is simple. Now we want to do even better, and we want to formulate this in Lagrangian optimization. Again, we have the same thing. We want to maximize this, and we can forget about 1 upon 2. It doesn't matter that much. And then these constraints. So we'll have same thing. So what we are going to do is that in order to minimize or maximize a function, the constraints, it's better to formulate this in terms of this Lagrangian formulation. So this is a function we want to minimize with these constraints, and we can put these constraints like this, and now we have one function as compared to these two things. And then whenever you want to minimize a function, you differentiate with respect to those variables. So we have variable here w, and then we have variable b. So we are going to differentiate this with respect to w, and as you see that this is square term, which is w transpose. So derivative of that with respect to w will become 2w, and this is the half here, so it will become w. And here w is in this term, so we'll get alpha I, yi, and derivative of w with w is 1, and then xi. And this one doesn't have w, this one doesn't have 0. So this is derivative of this with respect to w is this thing, which is very easy. Now we're going to differentiate this with respect to b. B is another parameter, and so this doesn't have b, and this doesn't have b. The only b is here, so it'll become alpha I, yi, okay? And derivative of b with respect to b is 1, so it'll become this. So derivative of this with respect to w has to be 0, derivative of this with respect to b has to be 0, so that's what we got. So which means that from here w is in terms of yi, alpha I, and xi. So yi, xi we know, but alpha I was Lagrangian multiplier, so which we don't know. And then from here we have a constraint that yi, alpha I has to be 0 from these. So far we have reached here. So now we are going to continue this, and we will substitute these what we found out, w and the other constraint. So this is the original thing we have. Now we are going to substitute w, which is shown here, yi, alpha I, xi, and this is the w, the dot product of w, so we'll have the yi, yj, so it's a summation here, it's another summation from the dot product, and alpha I, alpha j, and then we are going to substitute here also, so we are going to substitute in this one w here, so that another xi from here, and then we will have from here the plus alpha I, which is shown this one, minus plus, and then that will be simplified because this is a half of this whole thing and this is minus of this thing, so we will get minus half of this thing, and this is alpha I, which is, so we can write down like this. So that is what we got. So now we can look at this, the dual form of this original problem, where we have alpha I and these terms which are coming from here after substituting these two. Then we want to optimize this to find the alpha I, because alpha I we don't know. We know w now in terms of alpha I and the xi feature vector. So we will do again the quadratic optimization. This is again a function, and these are the constraints. Remember, these are the constraints we got from here, that yi, alpha I has to be 0, summation of that. So it's a similar thing. There we will find w. Now here we are finding the alpha, and again this is a constraint thing, and then you can use this quadratic optimization to get the alpha. Then alpha, once you know, then you can compute w. So that's that. So then just a summary is that we want to find alpha 1 to alpha n such that this is maximized with this condition that alpha I, yi is equal to 0 for all of alpha I. And so now we haven't talked about how to find b. Well, we know how to find w, how to find alpha. Next thing we want to find the b. Now we have to go back to the equation. Originally this is the equation we have. So in this equation, k is a label, it's a positive or negative, +1 or -1. W is the hyperplane, most parameters are hyperplane, and x is the feature vector, b is the scalar part of the hyperplane, should be equal to 1. And so we can rearrange this, bring in yk other side, so 1 upon yk, because yk is scalar, we can do that. And since yk is either +1 or -1, so this actually can be written yk 1 upon 1 or 1 upon -1 is the same thing, so we can do that, so like that. Then in this one, we know yk, we know w, we know xk, we can find b, and that's a b. Okay, so therefore the solution has this form, that we compute w in terms of this and b in terms of that. We have already computed alpha, then we are done. We have learned the SVM. And now in this thing is the important point here, that which support vector will remain, which will define this margin. And so originally we have to have this second term, we have the constraint term has to be 0 according to the math from these guys who came up with the Lagrangian conditions. So now this term is product of two things. One is this and other is this. These are the constraints, and this is the class in labels, and this is the alpha I. Now this can be 0 in two conditions. One is that this is 0, and then this one is greater than 0, but multiply with these to be 0. And what this means, when this is equal to 0, which means these are on the margin. These are at the margin. Okay, so if alpha is greater than 0, then these will be on the margin, and if alpha I is 0, then this has to be greater than 1. Okay, so therefore we are going to look at only non-zero alpha I, and they correspond to actually support vector, because this is very clear that the product has to be 0, and if alpha I is 0, then the two conditions, only first condition where alpha I is greater than 0, then we are going to pick those ones, and these are the ones which lie on the margin, and these will be the xi corresponding to those alpha I. Remember that each of the example, these are the examples, xi, x1, x2, xn, all these are the samples. Each of them have a label, yi, it's a positive or negative. Each of them multiplied by the alpha. So alpha is non-zero, then we are going to maintain those, because that's what they matter. If they are 0, they will disappear, and those are the other ones. It's a very nice, elegant formulation. It really works very well. So that is called the maximum margin, and so we know the W, we know the B, and they also only depends on the support vectors, and so the optimization problem, just to summarize, is that we want to find alpha i's such that this is maximized with these conditions and so on. This is just a repeat. So these are the once we have learned the classifier, then let's say we want to test the classifier, and we have this is the way we have learned. So we have xi, xj, as we talked about there. Now we have a test example x, which is a feature vector. So we are going to go through all those support vector, find a dot product with them, and for them, of course, alpha I is non-zero. We'll add it up, and we will get the f of x, and f of x is positive. It's positive class. If it's negative, it's negative class. So this is the test thing. And as you see, as you were asking earlier, that these are the ones we are going to use, those support vectors for which alpha I is non-zero. And that's it. So the testing in this SVM is very, very simple. It's very quick. It will just look at a few support vectors. Now, if the classifier is not good, then you may end up with lots of support vectors. If it's very nasty data, then you will, maybe in some cases you will have all of the example as a support vector, which is pretty bad. But most of the time you will have very few, and that's why you just find dot product with them, the feature vector, and you decide that. So now the next thing is then what happens when there's noise. So for that, the hard margin may have a problem, and so here are examples. These should be on this side and this should be on this side. So these are the misclassification. So for that we are going to do the next thing, which is actually even more interesting. That's what you're going to implement actually, which is called soft margin classification. And again, listen this very carefully. It's a very important part. So what we have here is the SVM. So we have the line separating these two classes, and this is the positive class, this is a negative class, and these are the constraints. This is what we have been talking about. Then let's say that we have misclassified, this x2, which is an open circle, should be on this side, x3, which is a closed circle, should be on this side, x1, which is open circle, should be on this side, but they have been misclassified due to noise and all these things. So we are going to look at the error, which is a distance from x2 to this margin, this line, and this error from here to this one, and this error from here to that one. So we want to minimize that error. So this is a different twist of the function we want to do, and which actually works better. So now we are going to do like constraint like this. We say that yi w transpose xi plus b should be greater than or equal to 1 minus eta I. These are the errors. These are the as compared to as we had there, which was just a 0. So we have 1 minus eta I, and eta I is positive number less than greater than or equal to 0. So that will help us to do better job. It will be soft margin, and of course these have to be small. And the interesting thing is that we can again do the quadratic optimization, because we always want to find w, and then now constraint is this one. We can just put that constraint here and then again use the same program. So the reason I want you guys to do the quadratic optimization in MATLAB, but that will be a very important tool you can use in many different places, and it's a very nice way to do it. And the reason this works so well, that this function we want to minimize or maximize is quadratic. Quadratic function are very bare function, and they have a unique maxima and minima. But if this function is not quadratic, then we will have problem, and we will not be able to minimize that function very easily. And that's the main point, and that was the big thing with SVM, that at the end, the way they formulated that it becomes a quadratic function, and then you can just use that, and works pretty well, and a very fast algorithm and so on. Okay, so then this is soft margin and old formulation, which was a hard margin. This is what we were doing. These were the constraints, and new formulation. These are the constraints, and so these are the differences, and then we can find out those etas and so on that you will do. So now, as we talked about before, that one is that what should be the C. C is kind of balancing, and this example from Andrew Zisserman. So if C is infinity, then it's a hard margin, okay? But if C is, say 10, then it's a soft margin, and you may have this misclassification there. But what happens that you learn C also using cross-validation. So once you learn the class, these W's, then you can take some examples for which and you can adjust. Typically, you can, for simplification, you can just C is equal to 1, and that I think will work okay. So that's that. So then we're going to talk about the kernel SVM, and as I told you last time, So this is a exclusive OR problem where we have feature vector is very simple. It's a two-dimensional feature vector, and it's a binary. It can be each of the element in the feature vector can be 1 or 0. So we have, say, 4 different combinations. We want to learn a classifier so that when 2 elements in the feature vector are same, whether both zeros or both ones, the output should be 0. When they are different, 1 or 0 or 0 or 1, there should be 1. So that's a classifier. It's a very trivial classifier. Now, so that classifier is very difficult to come up with one linear separation of these. As you see here, that we have these ones. This is 1. So this is, as you see here, the both are 0, and here both are 1s. So 0, 0 and 1, 1 from 0, 0 and 1, 1. Another example is here. X1 is 0, Y1, X2 is 1, and here X1 is 1, and X2 is 0. So there's no way you can separate these two things by one line. It's not possible. And this happens to be a very trivial example. It's called exclusive OR. And that was the one actually broke all the research people are doing under what is called perceptron. There's a very nice article in Wikipedia you should read about the perceptron research. The Professor Rosenwald from Cornell, he came up with this perceptron, and New York Times had a big headline that, and when it was supported by ONR, Office of Naval Research, and they had a press conference. They say, well, this will change the world, and this perceptron is a simple classifier which will all the computers, all the intelligence will be built on that can read, write, and understand everything. And so then Marvin Minsky and Pepper, they were doing at MIT the research, and they came up with this example. Say, well, perceptron cannot do this. This is very simple. And they actually wrote a book, Perceptron, which became very famous. Minsky wrote a book, I think. Minsky was the only author. And that really, slowed down the research. Now, other thing in perceptron is that it is like a neural network, early neural network. Very simple formulation. And that really slowed down all the research in this perceptron or neural network area for many years. As we talked about before, that the one problem with perceptron is that it will not deal with this because it's finding only linear boundary. The SVM, so far what we have discussed, will not solve this problem either. Other problem with perceptron was that convergence was slow, and they had a different algorithm to compute the W. Again, there they are computing W. And the other thing you have to look at, and we'll probably talk about a little bit about deep learning, which is very popular these days, which is neural networks. So neural networks also have these weights that you take different feature components and apply weights, you multiply it, and you get the output. So the classifier which we are learning here, the SVM, the W is the weights, and neural network has the weights, which is W also, and perceptron was also finding W. So that perceptron is the single layer network. Basically, it's just one layer. You take this and multiply weights, and you get the output. So now this thing is that the formulation of SVM came up with very elegantly in a mathematic formulation that you can formulate this optimization problem, you solve it using quadratic programming, but you show that the function you want to minimize is quadratic and there's a solution that exists and so on. As compared to perceptron algorithm was just iterative, heuristic, and it was converging to the right minima, but for only linear case, and linear classifier will not work for this kind of example. So so now the way to solve this problem is what is called kernel trick, that you take this data and map it to another dimension, another space, then you can solve this also, which is another very interesting thing in SVM. So as you see that here, you have these two classes, one of the red one, one of the black one. Now if you take the vector x1, x2, you map it to x1 multiplied by x2. So these points will map to like this. Okay? And now it's very easy, there's a boundary here. It's a very nice classifier. So the question is that how do you map this feature space, different feature space, then it becomes linear, then you solve that. So that is called the nonlinear SVMs. So you feel sleepy, huh? And not interesting. Yeah, I see. Okay, so the general idea is that we want to map to the higher dimensional feature space where training set is linearly separable. Suppose if you have this kind of data, this is impossible to find a linear boundary because this is a circle. You need a circle. Circle is not linear. But you map it to like this, and becomes very nice. You can separate by hyperplane. So this mapping is that we take the original feature vector x, we map it to using this mapping phi of x, and that will do the trick. Now we actually don't have to map, we will just do the dot product. Yeah, go ahead.
So how do we know what map?
Yeah, so we're going to talk about that. Yeah. So so now the mapping is a point that we want to do that, and then once we understand that mapping, our kernel, then this whole thing is very similar. The only difference will be instead of xi, xj, we'll have phi of xi, phi of xj, which is very nice. And then all these conditional phi, this all this. So again, the classifying function will be same, only difference will be the given example x, so it will be phi of x and phi of xi. So that's that. So kernel trick. So what we are going to do, that we actually don't have to map those, but because as you saw that what we need is a dot product, either xi xj or phi xi phi xj. So we just want to compute that dot product, and that in the linear SVM it's very simple, standard dot product. So kernel for this linear SVM is like this. That's what we should do. Now nonlinear kernel will be that we'll take xi, map it to phi of xi, take xj to phi of xj, then find the dot product. So now feature mapping is time consuming. There should be a light, is it right? Why do I need to put on glasses? Let's try the lights. Which lights I should turn on? Whiteboard or? All are on. Whiteboard. This is not good. This is good. For me, how about for me? It doesn't make a difference. Front. Can light. Anyway, so maybe I'm getting old, I think. Forget it. Okay. So the feature mapping time consuming, therefore we will just use the kernel directly, and and actually feature mapping is not necessary. Okay, look at the example and listen to this very carefully. Okay, so we have a two-dimensional vector x1, x2. This is a vector, feature vector, very simple. So kernel, we are defining that it will be 1 plus xi transpose xj. So we'll find the dot product of xi, xj, and whatever we get, we add 1 to that, then we'll square. If we were not using the kernel, then it will become xi, xj, xi transpose xj. This is simple dot product. There won't be a square, there won't be 1. So that is one possible kernel, and the way it's going to work is that in a way, if we apply this kernel, then what we are doing, we are taking this vector x1, x2, mapping it to this 6-dimensional vector. The first element is 1, second element x1 square, third is under root 2 x1, x2, fourth is x2 squared, fifth is under root 2 x1, and sixth is under root 2 x2. So that's actually the mapping which is happening. From 2 we are going to 6 dimension, and then if we do that, if we map the xi to like this and xj to this, then this is equivalent to applying this kernel. So let's look at this and we come back to that. So this is our kernel, and we have defined, we take the xi and xj, find dot product, square it, add 1 and square it. So let's expand this. So this is a vector, this is also a vector, two-dimensional vector as we saw. So we have to find dot product of these two, and we can do that. One is the xi1, xj1 first element, and xi2 and xj2 second element, square of that. So now we have to square this thing, and we'll say this one and this one, so it's like a plus b whole square. So this will become 1 square and b square, then 2 multiplied by 1 and this, so you know that. Then we need to expand this thing, and this will be 2xi1 xj1 and 2xi2 xj2. Then we have to square this again, so it'll become this square plus this square here, and then 2 this multiplied by that. So that's the expansion of that, and that, as you saw, is essentially the same thing when you take the take this one mapping, map x to this 6-dimensional vector, xi to this one, take the xj, map it like that, then this will end up exactly that I just showed you. And then this is what actually is happening in the mapping. So if you take this vector and this vector, find the dot product of this. So 1 multiplied by 1 is 1, xi square, xi1 square, and xj1 square, which is this, under root 2 multiplied by 2, xi1, xi2, xj1, xj2, which is this. And then we have x1, xi2 square and xj2 square, which is here, and then under root 2 multiplied by this 2 xi1 xj1, which is 2, which is this one, and then we have this final one, which is the 2 xi2 xj, which is this one. So what this is saying, that if we map the vector x like that 6-dimensional vector which is shown in the blue, then we can map xi like this and xj like that, find a dot product of that, which becomes like this. It is same as we are doing the mapping, that take the xi xj, find the dot product of xi xj, add 1 to that and square. So that is called the kernel, and this is a nonlinear kernel, and this is our phi, this is our mapping. So this is a particular example of the phi of x, and so there are two ways to do this. One way is that first we take the xi, map it to the 6-dimensional vector, and then we can multiply those and get like this. Other way is we can just directly evaluate this equation we have, and we will get exactly the same thing. So what we are always interested in SVM, that we just want to evaluate this the dot product. This is the, we want to evaluate this. So we actually don't have to do this mapping, we just have to find this one, the product, using this. So that is called kernel. So this is a kernel, this is our kernel, and this is if you don't do any nonlinear kernel, this is a linear kernel, simple dot product. If you do nonlinear kernel, then we will have to do something like this, and this is one example of that. So this whole thing is, as we saw, that kernel, what is doing is taking the two vectors xi and xj, and it is finding the result like that, and that is equivalent to taking the xi, applying the phi transformation where each xi will be mapped to 6 dimension, and taking xj, it's doing the same thing, and find a dot product. So it's two different ways to do that, and we will pick the one which is simpler one, and that's called kernel trick. So we already went through that, and there are many different kernels. So this is a linear again, and this is the called polynomial kernel. So there, as you remember, we were doing p was 2, you're squaring, but it can be 3, it can be 4, it can be 5, and so on. So that's a p is general. And this is called Gaussian radial basis function. So we'll take xi, xj, find the difference, magnitude of that, and then apply the Gaussian. So this is again Gaussian, you will see here very different application. And sigma is the parameter of this kernel. Here the parameter is p, which is the degree of polynomial. Then there are these other kernels, sigmoid kernel, which will take the beta 0 and beta 1, and then find the dot product of xi, xj, and then do the tangent hyperbolic or something like that. So then the nonlinear SVM, once you understand the linear SVM, is very, very simple. That this is the only difference is this thing, that instead of xi, xj, we have k of xi, xj, and that's the kernel. Then everything is the same. There's no problem with that. So as you saw, that we actually don't have to map the feature into higher dimensional space. We just have to know the kernel, and then we can do that. And it will deal with the nonlinear SVM. So training data, when they are separable, we can do the linear. When they are not, then we can do the kernel trick, and it will solve the problem. So these are the references, and this SVM was invented by this researcher. He was at AT&T, Bell Labs, which used to be called Bell Labs in US. That was a very famous research center historically, and lots of people got Nobel Prize from Bell Labs. Now it's unfortunate, Bell Labs doesn't have research center that much. but right now he's a professor at Rutgers, and he started, I think it's long time ago, 693 or something. They have series of papers, and this probably is a book. And then there are many websites you can get code for this, and then Andrew Zisserman has a nice link also. He has several examples of that, and I think the article in Wikipedia is pretty good. And then from Stanford University, Andrew Ning, he has a very nice write-up on that. So with all that, I think you should be able to really understand this fully well, and I think that's it. Yeah.
So we were talking previously about n-dimensional data, more than 2, and this is specific to just 2 dimensions.
No, this is not, because see this is just example we give for just to, get you feeling that what we are talking about here. This was a 2-dimension example. Yeah, but this is general. We're saying we take any n-dimensional vector and find the dot product of these two and add 1 to that. So this will be a scalar, then square that, that's the polynomial kernel. Then take any n-dimensional vector xi, subtract from x2, this is a vector, find the magnitude of that, and do the Gaussian, they'll become scalar, and same thing for here. So it's for any general vector. Yes?
So the xi and xj are the support vectors for the linear
Yeah, I mean, so see what we have done, that we are going to do this. So there are 2 ways to do this. One is that you will learn the kernel SVM, and you will tell that what is the kernel you are using. So you are using Gaussian radial Bessel function or polynomial kernel. Then the formulation when the support vector machine is going to do, so instead of just xi, xj, it will put a k xi, xj, that's it. Then you go through the whole thing, no change in the program. That's the only change.
So like xi, there are any 2 features in the...
Yeah, I mean, you see, you have lots of examples, and that's what you are doing. That this whole thing, we did the Lagrange multiplier and all these things, this whole machinery. But at the end, you can just take this one directly to your quadratic optimization and define what is this k, give it a k, kernel, then do the whole thing. And you should actually do that in your program. It'll be very good. There was another question.
How can we do multi-classification?
Yeah, so let's just let's understand just one class, then we will do multi-class later. But see, simple way is that you do pairs. You do if you have say 3 classes, so you will do 1 and 2, 1 and 3, and these pairs, and somehow you combine. There's lots of literature about that, but let's just limit the binary class. If you can understand that very well, then that's a lot. There was a question there first. Yeah.
I just to continue what you were saying.
Yeah.
Pairing is like if us 1 and 1 pair together, we say it's a right match.
Yeah.
Pair like 1 and 2 together is a
Yeah.
one. So
Yeah.
that's how we train this.
Yeah. So I mean, there are different things related to that, and the basic thing is that if we can do binary classifier, then multiple classifier is not that easy. You have a question?
You show different kernels,
Yeah.
and they have different behaviors.
Yeah.
For example, in the HOG,
Yeah.
which one is used, or in general, how do we choose?
Yeah, that I think is issue, but most of the time the radial basis function, the Gaussian one, works pretty well, and you can always try a couple of them and see what happens. I think this Dr. Chi has good slide talking about that. Let me actually show you that. As I told you, I have borrowed these slides from our new professor, and this gives an example of the impact of the kernels. So he look at this face gender recognition problem. There was some paper, and they did some study there. This is not mine. Yeah, I think I'm getting confused here. This one. So that give you some idea about the kernels and how do you select. So here is example. So that is the polynomial kernel, as you saw there, the first one on the left, and this is degree, because that's a parameter, what degree polynomial you want to use, and the error rate for this particular problem, how well you can classify female and male or overall. And this kernel is the radial basis function, and here the parameters, the sigma or gamma, and these are the different curves. So it is just, you will have to try and determine which degree is useful and so on. But most of the time, I think this radial basis function works pretty well. Yeah, go ahead.
The thing that I saw that we couldn't escape from the nonlinearity of our problem.
Yeah.
Displace the nonlinearity from, for example, that line to a map. So why don't we do something else instead of that line that we can classify our space? We just use another. Instead of line, we use another function, like second order function or third order function.
Yeah, so that's a good question, but see, the problem is that then it becomes, the problem becomes very hard to find that, see, like this one. So you're saying, let's find a circle to separate, Exactly. Yeah, but the, if you have the line, then this problem becomes easier, that you can show that you want to find the best classifier. You will maximize the margin or minimize W, and then it is a quadratic problem with constraint, and you can go through, find the solution. But here it will not happen. So you will have to find the equation of a circle, and that is not a linear. Circle equation, as you know, is x squared plus y squared is equal to radius, So it's not linear. You cannot do dot product. You cannot do all those things, So the reason we want to find lines is very easy. It's a dot product. We can find W, and we can.
We have this problem in our kernel.
No, kernel. What we are doing, and that's why it's called a trick. It's a kernel trick, which is interesting. So kernel, what we are doing, that we are taking the feature, we are applying kernel to them, then we are just treating them like a linear SVM. See? That's the main point. That's a very important point. So we have a feature vectors. So we learned all this. We can do soft margin, hard margin, all these things, linear classifier. That's it. So now we say, well, non-linear, we cannot do that. Like this example, it's very difficult. So what we showed here, that what we are going to do, that we'll take the feature vector, we will map it to the higher dimensional using this mapping phi, and then we'll find a dot product of phi of xi and phi of xj. Okay? So now we say, well, instead of the mapping these higher dimensional feature space, we are looking at, well, what we want ultimately SVM is in what form, is a dot product for two vectors. So we say, well, let's just map them, use this kernel that we want to find out the dot product of two vectors in the original space. Now we want to find the dot product of these two vectors in the 5 space. And we show that we can do that just very easily like that. And then that's it. Then we just treat it as a linear SVM. Exactly.
It still create a cost as we go to a higher dimension.
Yeah, but the main point here is that we even don't have to go to dimension, because our aim here is just find the dot product. And dot product of these two vectors we are getting using this thing very easily with the kernel. We even don't have to go there. We don't have to do mapping. Okay, so that's, it's a very smart way. That's why it's called trick. And so mathematically elegant, it really works. That's the idea. Yeah.
So the linearity doesn't happen in kernel trick, because the kernel trick is just the numeric values in a vector, and if we manipulate, like multiply, we still get the numbers. So it doesn't involve any non-linearity.
Yeah, the reason it doesn't involve, because we are applying the kernel so that, as I gave you an example, that in a way it is mapping this to the higher dimensional space. So see, if you go back, look at the exclusive OR. Okay, so this is a very simple example. So this is a nonlinear. There's no way we can find the boundary. Okay, but if we do this mapping to, even this is actually right now is in 2 dimension. x1 multiplied by x2. Okay, so this is a mapping. So we take a vector which has 2 components, and we get a new vector. First part of that vector is x1. Second part is multiplication of this, become this vector. Now if you apply this mapping, so phi mapping, to these points, they look like that, because as you know that this point here we have this point and this point will come here. So we are multiplying x1 x1 x2, so this one is positive, x1 and x2 is positive, so it'll become here. This one is x1 is negative, x2 is negative, again negative multiplied by negative is positive, and this is positive and negative, so it'll become negative. This is positive, negative, become negative. See, that's simple mapping. So that's a phi mapping. So we did that. Now it's a nice boundary we can get. So the reason we are able to do that, in principle we are doing the mapping as we did here. Mapping makes it linear, as you saw here. And this is not necessarily just 2 dimensions can be in there. Then we say, well, what does mapping means? What's the impact of mapping in our formulation SVM? We say, well, we only have to worry about this whole thing reduces to, we are finding a dot product of these examples, xi and xj. Linear SVM find the dot product xi, xj. So now there are 2 ways to do it. One is that we take xi, map it to phi xy, take xj, map it to phi xj, and then find that. Other way is that, well, we don't have to map it, we just want to find what is the dot product in that other space, and that's what this is doing, and which is very nice, very good, and it solves the problem. Okay? Give him a chance.
I
Yeah.
think it's a very serious problem to find the mapping function of the one coordinate to another coordinates. I mean that if in the hyperdimension, so many dimensions, it's a problem to visualize the vectors, because we can visualize this into the 3-dimensional or 4-dimensional, at most at the color or time dimension. So it's not very easy to visualize them. So it's not easy for us to imagine what is the distribution of this data should be like. So we can't build up very precise pattern for the mapping. So will be a very, very time-consuming method to try any which is the best mapping method. So this will be very time-consuming. So
Yeah.
this is the problem.
Okay. Yeah. So that's that's right. That's a good point. So, but see, the idea is that in math or in science, you need to understand the concepts, the theory. And for humans, it's easy to understand, say, in 2 dimension or maybe 3 dimension. So once you understand, you are convinced, then you blindly, extend to n dimension. That's the whole thing. Is that you can do many dimension. It has to work, So now there are these kernels which people have tried, and they are known and they work better. But in order to visualize, if it's a high dimension, one thing you can do PCA maybe to reduce and so on. But most of the time, you just use the known kernels and see what's the performance you're getting. You pick the best one, as we saw here, that you can take polynomial, you look at degree of polynomial. If it's 1, what's the performance, 2, and so on. And that's okay. You can find out from the class validation, because you know what you are expecting, and see, well, if I do 1, what's the performance? If I do 2, what's the performance? You pick the 1, which is better. So there is something, but you don't have to, because see, the whole idea is that everything has to work by a computer, and this is getting very close to that. Yeah, one last question.
Is there more samples needed to increase the amount of dimensions? Because you're kind of giving more, places where the data can go.
Yeah, because see that it's a matter of the unknowns, right? So you have W is a vector, so W1, W2, these are the unknowns, and you have alphas, so you have to have enough samples to get to solve this problem. If you don't have enough sample, then then you won't be able to solve this problem. In general, more samples you have, better it is, because it's you are in a way minimizing the error, square of error. Again, here it's square of errors, right? Eta was square of error. So more examples you have, better it is. But these examples have to be correct. If they're noisy, then it's a problem. Also, but many times it's not possible to get lots of examples. So that's why there's a whole area of research which is called K-short learning. So can you learn a classifier using only K examples, say 2 examples or 3 examples, So there's a whole research there. But in general, these are the training-based approaches, so they need lots of training data. More data, better it is. Okay, so we are going to stop here.